What the heck?
Tagon.
Hello, my beautiful audience. It's been a little while since I've put up a video. You can see I'm back in my normal spot. I think I'm not going to bother with this board during regular videos, and I'm going to go back to my top-down view. First of all, I think it's more convenient, and not to mention the board takes up the entire space of the screen as opposed to just being a vertical slot in the middle, which can be a little hard to see by comparison. So I've just been busy, holidays, family, lots sort of just happened in the last few weeks, so I've been a bit distracted. Today we're not going to do anything particularly crazy. I just wanted to bring back something that I think some of you might have missed, and that would of course be
Monday Math Nuggets.
Yeah. It's just going to be a simple little video. I want to explore the idea. By the way, this is inspired by a Dr. Payam video from probably a couple years ago now, asking a funny little differential equation question, and that's essentially what this is going to be today. I want to find functions that when you take the inverse of their derivative, you get the antiderivative of that function. So say you differentiate a function and then you invert that new function, that new derivative, you get the antiderivative of the original function. And so we're going to see if we can discover any types of functions that satisfy that relationship, and we're probably going to make a simplifying assumption, or else it might get a little bit difficult. But let's go. Okay, so as I said in the introduction, what we're going to do is we're going to look for functions f of x with the following properties. So f of x such that if we take the derivative, if we take the derivative of f of x, and then we invert that, so I'm just going to do NIV, or INV for invert. That just means, take the inverse function, whatever the inverse of the derivative of f is. Then I want to find f of x's that satisfy the fact that the inverse of its derivative is in fact its antiderivative. So of course that means that capital F of x, if you take the derivative of that, you just get little f of x back. So another way to frame this is to simply take the derivative of both sides, and so you have the derivative of the inverse of the derivative of f is f again, because if we took the derivative of this, we get little f back, right? Because that's what the antiderivative of a function is. Now, to try and solve this problem in general might prove to be either maybe it's impossible to do it analytically, I'm not too sure, but I know that in the video that I referenced that Dr. Payam made, it's not Joe this time, it's T. Joe, but this video that Dr. Payam made, he sort of assumed that it was a polynomial, right? It was like a single power of x multiplied by a number. And so that's what I'm going to do. So if we say that f of x is equal to a times x to the power of b, we can now determine the three things that we need to know. We need to know the derivative of that thing, we need to know the inverse of that thing, and we need to know the antiderivative. Well, the derivative is very easy. If you know any calculus at all, it just brings the power down and the power decreases by 1, since it's a derivative with respect to x. Again, a and b are just any numbers you want. So we're going to get a times b times x to the power of b minus 1. And of course, if we do the antiderivative, we just do the opposite of that. So we raise the power by 1 and divide by the new power. So we get a divided by b plus 1 times x to the power of b plus 1. And now the inverse is pretty easy too, the inverse of the original function. Say you swap x and y and you solve for y, you're going to have to divide by a and then take the 1 over b power, which means the inverse of anything that looks like this is simply x divided by a to the power of 1 over b. And so now that we have all of these facts, these are essentially the only necessary tools we're going to need. And so what I'm saying is, if I take the inverse of this derivative, I want to end up with the antiderivative of the original function. So I can set the inverse of this function by using this tool, right? But just because this is different from this thing here, this idea of dividing by the coefficient and doing 1 over that power still applies to this term here, right? Because a times b is just the a in this case, and b minus 1 is just the b in this case. And so I would just replace those things with those things. So the a here would just become a times b, and the 1 over b here would be 1 over b minus 1. And that would be the inverse of the derivative. And I want to say that that's going to be equal to the antiderivative. And so let's make that a little bit more explicit. So in this case, the inverse of the derivative of f is going to be, so this is the inverse of the derivative of f, and this is going to be equal to x over ab to the power of 1 divided by b minus 1. And I'm saying that I want this to be equal to the antiderivative of this function, which comes out to be, of course, the same thing there. So we get a divided by b plus 1 times x to the power of b plus 1. And of course, the only way that two polynomial terms can be equal to each other is if their coefficients are the same and if their powers on x are the same. And so we can solve part of this problem by first looking at the powers of x. We see that we have b plus 1 and 1 over b minus 1. Since we want to set these things equal to each other, those powers must actually be the same. So we have the result here that b plus 1 is equal to 1 over b minus 1, which tells us quite clearly that if we multiply the b minus 1 over, we do difference of squares, and we get that b squared minus 1 is equal to 1. And of course, that tells us that b squared minus 2 is equal to 0, which is a very simple quadratic equation to solve, and that tells us that b can either be plus or minus the square root of 2. Those are the only powers of the original function that we can have where what I'm declaring to be a property of that function holds. So the only way that this thing that I'm saying, the inverse of the derivative being the antiderivative, the only power of x, if it were a single polynomial term that would work, are positive and negative the square root of 2, which is a little interesting. I believe in Dr. Payam's video it involved phi, right? 1 plus root 5 over 2, as opposed to the square root of 2. I guess you could call it phi as well, since we've bastardized p and turned it into pi. But the last thing we have to do is, okay, so we know that b can be plus or minus root 2. That's nice. But what we should do is we should try and solve for a now. Because now what we need to do is we need to set the coefficients equal to each other and then put a entirely in terms of b, which will allow us to simply plug in the values for b and get our two possible answers. So let's do that now. So we know that b is equal to plus or minus the square root of 2, and we're looking for a and b such that x divided by ab to the power of 1 over b minus 1 is equal to a divided by b plus 1 times x to the power of b plus 1. And of course, we just solved the fact that b is plus or minus the square root of 2. That's the only option, by setting these powers equal to each other. But now we want to set the coefficients equal to each other. So to do that, we need to isolate what the coefficient is here. And it turns out it's not too hard to do. We just end up with ab to the power of 1 over 1 minus b, right? Because before it's 1 over ab. But if I reciprocate that and make it just ab as opposed to 1 over ab, then I have to make the power negative. And so the negative of 1 over b minus 1 is 1 over 1 minus b. So that is the coefficient here, and of course the remaining part is the x to the power of 1 over b minus 1, and the fact that we have the two powers of x here, we set them equal to each other, and that's how we got this result here. So now all we need to do to solve for a is to set these equal to each other. Not too bad. And so we end up with a to the power of 1 over 1 minus b times b to the power of 1 over 1 minus b equals a divided by b plus 1. So we're going to divide the a on both sides, and we end up with 1 over b plus 1 equals a to the power of 1 over 1 minus b minus 1, right, because we're dividing a on both sides, times b to the power of 1 over 1 minus b. Hope that's clear so far. And now what I'm going to do is I'm going to multiply this thing over to the other side, which means we're going to get b to the power of 1 over b minus 1 right up here. So that tells us that a to the power of 1 over 1 minus b minus 1 is equal to b to the power of 1 over b minus 1 divided by b plus 1. I hope that's clear so far. I'm just manipulating the expression. Now I want to simplify this here, this power, because there's no reason to leave it as this difference of two different terms. What I'm going to do is I'm going to rewrite 1 as 1 minus b over 1 minus b, and then I'll be able to combine them together. And so we're going to end up with 1 minus 1 minus b divided by 1 minus b as the power. And so that just becomes b over 1 minus b. Cool with that so far, I hope. And what we're going to do now is we just want to solve for a, right? So we're going to raise both sides to the 1 minus b over b power, right? So we're literally just going to, raise both sides to that amount. 1 minus b divided by b. These two powers are going to cancel by construction. And we're going to end up with a is equal to, so this 1 minus b and this b minus 1, them dividing by each other in the power simply gives you negative 1. So we're going to get b to the negative 1 over b in the numerator, b to the negative 1 over b, divided by b plus 1 to the power of 1 minus b over b. We can sort of rewrite that so that the powers look a little bit nicer. And we end up with b plus 1 to the power of b minus 1 over b divided by b to the power of 1 over b. All I did was make both of the powers negative and swapped their positions. But of course, all that you need to do now is simply plug in plus or minus the square root of 2 into this expression here, and we just gotta see what happens. So let's plug it in. I don't know what these two things are particularly equal to, but Wolfram Alpha knows, of course, and I will simply plug them in and tell you what those approximate values are. And so since these are the two solutions for A, in terms of B, we can plug them into Wolfram Alpha, of course, and we get a nice little approximation for these things. And so the coefficient A for when B is positive square root of 2, the power is positive square root of 2, the coefficient A is just about 1.0131, and that just sort of goes on forever. Of course, it's probably horribly irrational. And when we plug in negative square root of 2, we end up with a complex number, I believe. So this number, this complex number, which would be an interesting power, an interesting coefficient, right? So the power would be negative root 2, and that's totally fine. You know, that would be fine for real numbers. But the coefficient, where the power, if the power was negative root 2, the coefficient A is a complex number. This is a complex number, and it turns out to be 0.0755 plus I times 0.2735. And so these, B, the powers of the functions whose, if we assume our function is a polynomial term, then those things that satisfy the result that the inverse of the derivative is the antiderivative require that the power of that x is either positive or negative square root of 2, and when you pick those two things, you end up with the two results for the coefficients A of those terms. If you pick positive square root of 2, you end up with a real number, about 1.013, and if you pick the power of negative root 2, you end up with a complex coefficient, about 0.0755 plus I times 2735. And so, of course, you end up with the final answer. So this is A times x to the power of B. And these two options are the two polynomial terms that satisfy this relationship that I will again say is that the inverse of the derivative of the function is equal to the antiderivative of the function. I'm sure there are maybe other things that satisfy that relationship, but it would be probably very analytically difficult to solve for. But anyway, thank you for watching this reboot, this reboot of Monday Math Nuggets. I hope it was enjoyable. It was a neat little problem to solve, and you get some pretty cool numbers out the end. All right, so I'm going to go back to pretty regular video making now. The holidays are over, and now we can get back to the math, of course. I would like to say and encourage my viewers to join me in a challenge that I'm doing. If you follow me on Instagram, @WhatTheHectagon, then you'll know that I'm doing a 52 books in 52 weeks challenge, reading one new book every week for the entire year of 2021. Currently, I am reading Brian Greene's third book, The Hidden Reality. And after that, I will probably be reading, I think, A Clockwork Orange, and then One Flew Over the Cuckoo's Nest, and then I think The Exorcist after that. I have to pick relatively short books, or else I won't be able to finish them in time. But I'm doing this challenge because I have plenty of things that I want to get reading, and I encourage you to do the same if you are so inclined. I'm also reading the Bible, which is sort of fun, but that's not included in those 52 books. There's like little bits in the backs of it where it's like, read this much every day, and that's what I'm doing just as an intellectual exercise and a test of my willpower, if you will. So I encourage you to read. That's all I'm trying to say, because that's what I'm going to be doing for much of the year. So thank you very much for watching. I will see you all very soon. Happy mathing. Goodbye.